This is day 68 in Calculus 1. We're going to run through a few practice problems since I won't be able to make it into class today. In this first set of problems, we've been asked to approximate the area underneath the curve over the given interval using 4 left endpoint rectangles. And what's nice about this one is that the rectangles have already been created for us. So we literally just need to compute the height of the rectangles, recognize the width of the rectangles, and then find the total area. Now you may notice that on the example on the left-hand side, I didn't know how tall each of these rectangles were, so I actually computed what the result of each function was for each individual rectangle. On the example on the right-hand side, we have the heights already pretty well identified for us. So without consulting the equation above, we can say that the area or approximate area underneath the curve in this interval would be equal to the delta x, which is 1, times the height of 8 plus 11 plus 12 plus 11. And again, I'm getting each of those heights from the measurement of each of these bars. And I could take this to the calculator or do this by hand. It appears that the area is equal to 42. In this example, we're again finding the area or approximating the area under a curve. This time we're using 4 right endpoint rectangles. And again, it doesn't appear that we really need to consult the equation too much. The height of each of these rectangles is pretty clear. They come out to be nice whole numbers. The resulting calculations in the function on the left, however, would not have been whole numbers. So again, that's why I'm showing the math over here for each individual function result. And it appears in this case that the total area is approximately, or is 22, using this approximation method. And in this example, we're approximating the area under a curve. This time we are using 4 midpoint rectangles. And on this equation, since the height of the rectangles is unknown, it will be a good idea to go ahead and compute what each one would be. So in general, again, we know that the area is equal to the width of each rectangle. In these cases, the width has always been 1, times the height of each individual rectangle. Now, since we're approximating the area between a -6 and -2, and these vertical bars represent the edges of each rectangle, we want to find the height of each rectangle right there in between each of those edges. So I'm going to calculate the height at -5.5. We'll calculate the height at -4.5, and so on. Now, I don't think it's really necessary to calculate each of these heights individually. We've got a nice graphing calculator available to us, and if I were to ask this question on the test, this would definitely be a calculator permitted, because we'll get some decimal results here. So I'm going to go ahead and cut away to what the calculator would look like. Feel free to pause to verify that I have set up the expression or the equation appropriately. And here we have the calculator. Again, I have the rectangle width 1 times each of the function results. And so this is -1 divided by x for each x value from -5.5 up to -2.5. And when we press enter here, since I used decimals to begin with, my end result is a decimal as well. And since the instructions weren't that clear, we'll go ahead and round this to the hundredths place. 1.09. We've got just a couple more area approximations. Let's use these tables for area approximations, and then we'll continue on another video. Now the instructions here say to use a left-hand Riemann sum to approximate the integral based off the values in the table. And one thing I do want to point out is that the intervals in this table are not consistent. And that's pretty unusual for us, but it's not something that we can't handle. We just have to be a bit more selective in how we visualize this. So you can see what I did over here on the left-hand side. I started with just a quick sketch of what the equation might look like, or what the graph of this equation might look like. And I'm going to mark the x values on the x-axis and the y values on the y-axis. And I just counted up by ones along the y-axis. And now I'll actually place some points for each of these coordinates. So 0, 3 is going to be a point, 4, 2 is a point, 5, 4, 9, 5, and then 10, 7. Now if I wanted to, I could connect all of these with a curve to try to get a better visualization of what's going on in the function, but to me that just gets in the way. I'm going to create my left-hand sum based on these data points. And as you recall, the left-hand sum only requires the first 4 data points. We don't include this last one. So I must create these rectangles based on the data point that appears on the left-hand side of each interval. So we'll use that data point, this one here, and this guy, and then finally this one. And it might be a bit tough to see at first, but what we have here in this first spot is a rectangle that's 4 units wide and 3 tall. In this rectangle we have one that's 2 units wide and 1 unit tall. I'm sorry, 1 unit wide and 2 units tall. In this example here, we have again 4 units wide. This time the height is 4. Again, I'm getting these heights from the data points in the table. And this last one, this last approximation, is 1 unit wide by 5 units tall. So the total area is the sum of each of these. 4 times 3 plus 1 times 2 plus 4 times 4 and 1 times 5, which sums to 35 square units. Now I'll complete this final example, the right-hand Riemann sum, without any commentary. I'll just show you the work, and hopefully you'll be able to follow along. If you're having a bit of trouble, make sure that you review the 3 other examples that you can see in the screen, and catch me before the start of the day tomorrow, and I'll try to clarify. And it appears that the total area for this example comes out to be approximately 68 square units. So that takes care of all of the practice problems I wanted to cover with approximate areas underneath the curve, using left and right hand, and also including midpoint sums. In the next video, I will discuss different ways or the appropriate method to find definite integrals or exact area under the curves using antiderivatives.